morning, dear students. Welcome back to my class, Ionic Equilibrium. Today I am going to discuss about the common ion effect and the solubility product, the two concepts of in analytical chemistry. Okay, and the application of these two effects in the analytical chemistry or in the salt analysis. Okay. First of all, we have to discuss what is common ion effect. So directly I am going to the definition. All of you know the case of a weak electrolyte in their aqueous solution, they exist partially ionized in their solution. So the peculiarity of any weak electrolyte is that they can exist in partially ionized form in their solution, and there exists an equilibrium between the ions and unionized part of the electrolyte. That is the situation of the weak electrolyte. Okay, suppose, so we have an equilibrium constant there, which is always a constant that exists between the ions and the undissociated part of the electrolyte at a particular temperature. Suppose we add another electrolyte, a strong electrolyte containing an ion common to that of the weak electrolyte. That is, the presence of the common ion can suppress the ionization of the weak electrolyte in order to keep the equilibrium constant the same, or to keep the K to keep it same at that particular temperature. The equilibrium shift towards left, that is more undissociated weak electrolyte is to be formed in order to keep K constant. That means the resultant fact is that the dissociation, the extent of the dissociation of weak electrolyte is considerably suppressed. So that is the actual case. Consider the case of generally the ammonium hydroxide. All of you know that ammonium hydroxide. It is a weak electrolyte. It can exist as partially ionized form in the water molecule NH4 plus OH minus in the aqueous system. Okay, so that this is the ions, ionized species, and this is undissociated, so undissociated part, and the equilibrium constant K, you know this K. B, here it is called Kb, is equal to concentration of ammonium into concentration of OH minus divided by the concentration of undissociated ammonium hydroxide. It's a constant at constant T. So Kb is a constant temperature. There's a definite value of ammonium, OH and ammonium hydroxide there at a particular temperature. Suppose we add another strong electrolyte like ammonium chloride in the water. You know that ammonium is a source, is a strong electrolyte. You can furnish a large amount of ammonium and chloride ion. And this ammonium ion is an ion common to this ammonium hydroxide. So suppose we are adding ammonium chloride, it will furnish ammonium ion, which is an ion common to the ammonium hydroxide, so that the concentration of ammonium ion increases, so that Kb tend to increase. So in order to keep Kb constant, so the presence of ammonium increase the concentration of ammonium ion, so that Kb tend to change. So in order to, Kb is always a constant. In order to keep Kb constant, what is to be happened? That is, ammonium, the increase the ammonia ion is to be reduced. That is by shifting the equilibrium towards left. That is, more undissociated ammonium hydroxide is produced, and thus keeping the ammonium ion concentration constant or Kb constant. That means the effect is that the dissociation of ammonium hydroxide is suppressed, or the equilibrium shift towards left means the dissociation of ammonium hydroxide is suppressed. That is another example. Is another case. You consider the dissociation of acetic acid in water. Okay. acetic acid and dissociate as CH3CO minus plus H3O plus. So that the equilibrium constant Ka is equal to CH3CO minus into H3O plus divided by undissociated acetic acid. This equilibrium constant K, dissociation constant K of the acid is always a constant at constant T, as you know that. But if you add another salt, that is sodium acetate into it, CH3CONa, into the system, the CH3CONa can furnish large amount of acetate ion and Na plus ion. This acetate ion is an ion common to the acetic acid. Also, when we add sodium acetate, which is a salt that can furnish acetate ion in larger quantity, so that the acetate ion concentration increases. The acetate ion is an ion that is common to the acetic acid, so the increased concentration of acetic acid will change the value of Ka. So in order to keep Ka constant, you know that Ka is always a constant. In order to keep Ka constant, the increased acetate ion needs to be reduced by shifting the equilibrium to its left, so that is undissociated, more undissociated acetic acid is produced. That means dissociation of acetic acid is suppressed. That means in this case, by adding sodium acetate, we can shift the equilibrium to its left, that we can suppress the dissociation of acetic acid by adding an ion common to the acetic acid, that is sodium acetate. Similarly, we can suppress the dissociation of ammonium hydroxide by adding another electrolyte containing a common ion, that is like ammonium ion, so that we can suppress the that is dissociation of ammonium hydroxide. So generally, this phenomenon is called the common ion effect. That is the process or the phenomenon or the suppression or the dissociation of a weak electrolyte in its solution by adding another electrolyte containing a common ion or the weak electrolyte into it is called the common ion effect. That is the definition. So the process of the suppression of a weak electrolyte in its solution by adding another electrolyte, usually strong electrolyte, having an ion common to that of the weak electrolyte into the solution is called common ion effect. Example, the dissociation of ammonium hydroxide can be considerably suppressed in the solution by adding ammonium chloride, because ammonium chloride furnishes the common ion, ammonium. Similarly, the dissociation of acetic acid in solution can be suppressed by adding sodium acetate, that is which contain the common ion acetate ion. So in any cases, we can suppress the dissociation of hydrogen sulfide, hydrogen H2S. We can suppress the dissociation of H2S by adding an ion containing H plus ion or sulfide ion, any kind. Okay. So that is the case. The hydrogen sulfide aqueous solution provide 2H plus 2H2 minus. We can considerably reduce or suppress dissociation in the presence of HCl. The presence of HCl, because HCl can furnish the common ion Cl minus, so that the equilibrium shift towards left. So we can suppress the dissociation. So the important effects, the application of the common ion effect is that we can apply this principle in the analytical chemistry. Okay, that we are going to the aspects after discussing the solubility product also. So first of all, you study this definition and with the example. The process of the suppression of a weak electrolyte in its solution by adding another electrolyte, usually strong electrolyte, containing an ion common to that of the weak electrolyte in the solution, okay, is called the common ion effect. Example, we can suppress the dissociation of ammonium dioxide in the solution by adding ammonium chloride, which furnishes the common ion ammonia. Similarly, we can depress or suppress the dissociation of acetic acid in water by adding another electrolyte containing a common ion, that is sodium acetate, in the solution. That is the common ion effect. The next is solubility product. The solubility products. Consider a saturated solution of a salt. Consider a saturated solution of any salt, like, okay, AB, a binary solitary AB, solid or salt, in the solution AB saturated, okay, that will dissociate to A plus B minus, like this, okay, anyway, or A minus plus B plus, like this. So what is the peculiarity is that in the saturated solution of a salt, there is always an equilibrium between the ion of the salt with the undissolved part of the salt. That's the peculiarity. That a saturated solution of a salt is an equilibrium. It's an equilibrium. It's a state of equilibrium. The saturated solution of a salt is a case of equilibrium in which the ion of the salt in the solution always is in equilibrium with the salt in the saturated state, undissolved part of the salt, which in turn is in equilibrium with the solid part of the salt. Okay, that is the thing. In the saturated solution, there is always an undissolved solid salt is there. The undissolved salt always lies in equilibrium with the dissolved ion of the solution, dissolved ion of the salt. So that by applying the law of mass action, we have the equilibrium constant K is equal to concentration of B plus aqua into concentration of A minus aqua divided by the concentration of AB solids. The concentration of AB solid is always a constant, it is unity, so we can write K into AB solids can be taken as KSP, that is called solubility product, that is obtained as the concentration of B plus aqua into the concentration of A minus aqua in the solution. And this product is called solubility product. What is this product? This is the product of the ionic concentration of the salt. The product of the ionic concentration of the salt in the solution. So the product of the ionic concentration of the salt in a solution is always a constant in a saturated solution and at a constant temperature, and that constant is called the solubility product. So KSP, the solubility product of a salt, is defined as that is the product of the ionic concentration, the product of the concentration of the ion of the salt in a solution is always a constant at constant temperature in a saturated solution at a constant temperature, and that constant is called a solubility product. Okay, that is the situation. That is at constant temperature in its saturated solution. That is very important. So what is solubility product of a salt? The solubility product of a salt is defined as a constant, which is the product of the ionic concentration of the salt solution in a saturated solution or in the saturated solution of a salt. The product of the concentration of the ions of the salt is always a constant at constant temperature, and that constant is called the solubility product. Okay. So it has two other aspects. That means in the saturated solution, we know that in the saturated solution of a salt, the product of ionic concentration, is equal to solubility product. But the product of ionic concentration is less than Ksp, solubility product, if the solution is unsaturated. Okay. So we got the second condition. That is, if the solution is unsaturated, that means the product of the ionic concentration now is less than Ksp. 3. That is, if the solution is supersaturated, means that the product of ionic concentration is greater than or exceed solubility product. That we got 3 different conditions with respect to the ionic product of the ionic concentration and Ksp. So the case of a solid solution, there exists 3 conditions between Ksp and ionic products. Ionic concentration, or the product of the ionic concentration of the salt. That is, in the saturated solution, the product of the ionic concentration is always equal to the solubility product Ksp of the salt at a particular temperature. But in the unsaturated solution, case 2, in the unsaturated solution, the product of the ionic concentration is lesser than Ksp at a particular temperature. On the other hand, in the solution is supersaturated solution, the product of ionic concentration exceed or greater than the solubility product. Okay, and this situation is very important. That is, saturated solution is a limiting case in which the salt is dissolved up to a maximum extent, so that there is an equilibrium between the ions of the salt with its undissolved part. On the other hand, in the unsaturated solution, the product of the ionic concentration is lesser than Ksp, means that more and more salt solutions, so salt is to get dissolved in the solution. But if the product of the ionic concentration exceeds Ksp in the supersaturation, means that the solution, more dissolved part of the solution remain as undissolved part, or the more of the solute get precipitated in the undissolved form. More of the dissolved part of the salt get precipitated in the undissolved form in the supersaturated solution. So that the supersaturation condition is to be created. Suppose you want to precipitate a dissolved part of the salt in the solution, we have to create a supersaturated condition. Okay, that aspect come in the analytical chemistry for the precipitation of certain cation in the form of their suitable precipitates by adding suitable reagent. But that aspect is to be discussed. So next we have to discuss the expression for the solubility product. There is an expression for the solubility product with respect to the concentration of the salt solution. So consider a binary salt solution like AB. I have mentioned about the AB solids. The solids exist in the saturated solution. AB is saturated solution. Okay. is an that is a okay, that is a intermediate state that will exist as a b plus aqua plus okay, that is, I think it is a b a solid plus here b a saturated solution plus b plus aqua plus a minus aqua. Okay, in this case we have the equilibrium KSP. Now that is concentration of b plus aqua into the concentration of a minus aqua in the solution. So this is the solubility product at a constant temperature. Okay, suppose S is the solubility where B plus aqua represent actually the solubility, the ionic concentration B plus represent the solubility of that salt, okay, with respect to B plus ion, and the A minus aqua represent the solubility of the concentration of A minus aqua, and it represents the solubility of this salt. Suppose S is the solubility of the salt, S moles per liter. S moles per liter is the solubility of the salt. S is solubility of the salt in the moles per liter. Then we have the equation: 1 mole of Ba solid or at dissolution gives 1 mole of B plus ion and 1 of A minus ion. Similarly, S moles of Ba on dissolution gives S moles of B plus and S moles of A minus ion in the solution. So by S is solubility we have Ba. So S is solubility we have that is here S is S moles per liter. So we have the KSP. Solubility product is concentration of B plus is S into concentration of B minus A minus S is S. So that is equal to S square. So solubility product is equal to S square. Therefore S is solubility S is equal to square root of solubility product. This is the case of a binary solute. But you consider the case of any unique divalent in applied, like AB2, like BA2 solid. Okay, BA2 solid. That will remain BA2 solution saturated solution that will dissolve still gives that is 1 B2 plus 2 A minus. This is the situation. This is the situation. Suppose S is the solubility, you know that 1 Ba2 plus give 1 B plus ion, 2 plus ion and 2 A minus ion. Therefore S is the solubility, it will give S and 2S. S and 2S A minus ion. K solubility product is equal to, you know that concentration of B2 plus into concentration of A minus the whole square. This situation. Therefore the solubility B2 plus ion concentration S into the concentration of 2A minus ion is, that is equal to A minus ion is, that is 2S. Concentration of the A minus ion is 2S, the whole square. So that is situation. So that is equal to 4, okay, S cube. 4S cube. Therefore S is, that is KSP by 4. Solubility product divided by 4, the cube root. This is the situation. KSP by 4. So consider generally the case. Generally we have the equation. Consider a general salt to the type. General salt to the type, that is in the situation, that is BMANS. BMAN. Solid. Okay, the saturated solution gives BMN saturated. Okay. That will gives okay, again. As for BMAN BAN, solid. BMAN, saturated solution, that will dissociate give. Okay. MBN plus NaM minus. Suppose this is the situation. This is the situation. So this equation is like this. The solid BMAN exists in the solution, the saturated solution as MBN plus aqua plus NaM minus aqua. Therefore, KSP, the solubility product of the salt, KSP is equal to the concentration of BN plus aqua, the whole raised to M, into the concentration of A, M minus 1 aqua, the whole raised to N. This is a situation. Suppose we have seen that if S is the solubility of the salt, if S is the solubility of the salt in moles per liter, we have the solution. Do you know that? We have this is the concentration. Okay, this is MS and this is NS. Okay, if S is the solubility, the concentration of B plus ion is MS and the concentration of A minus N is NS. Therefore, we have the equation that is equal to B concentration of Bn plus ion is, concentration of this Bn plus ion is MS raised to M into the concentration of I minus ion is NS raised to N, concentration of NS raised to N. This is the situation. So we have the equation that is M raised to M into N raised to N into S raised to M plus N. S raised to M plus N. This is the situation. Okay. We have the equation that is M raised to M into N raised to N into solubility raised to M plus N. Correct? M and N are numerical number. M and N are integers. Okay. Therefore, the yes, solubility of the salt is. Solubility of the salt is. What is solubility of the salt? Yes, KSP. KSP divided by M raised to N into M raised to M into N raised to N. Okay, S raised to M plus N. S raised to M plus N is like this. Therefore, S is equal to the root of M plus N root of M plus N root of M plus N root of KSP divided by M raised to N into N raised to N. This is general thing. Where M and N are not the charge of the ion, but only the number of moles of the ion. Remember, M and N here indicates the number of moles of the ion. That is always an integer. So you don't look into the charge of the ion. Okay, that's the thing. So in the case of calcium chloride, what is the situation? Calcium chloride. Here 1 plus 2. S is equal to solubility. S is equal to saturated solution. The solubility S is equal to square root of 3 raised to KSP by 3. Okay. The case of AlCl3. Okay. Al2SO4. Thrice. Al2SO4 thrice. What is the situation? Saturated solution. That is S is equal to here 3 plus 2 square root of 5 into 5 root of Ksp by 5. That is the situation. Similarly, the case of any such salt, we have this equation like this. Okay. Calcium phosphate. We have the case calcium phosphate. Ca3PO4 twice. Calcium phosphate. We have the equation. Okay. Ca3, Ca, 2Ca, 3Ca2 plus aqua plus 2PO4, 3 minus aqua. So in this case we have the equation S is equal to like this. Okay, Sp or the salt divided by 5 by m raised to m. Oh, that is some. Here is some m raised to m. Okay, m raised to m. This some wrong mistake is there. This is m plus n raised to, what is the situation? Okay, some mistake is there. Calcium chloride, that is 1 raised to 1 plus 2 raised to 2. 4. Split by 4. Here it is become 2 raised to 2 into 3 raised to 3. Another number. This is the situation. 27 into 4. 108. So the situation is, in this case, is 108. 108. The case of calcium chloride, lead chloride, etc. The case of calcium chloride, lead chloride, etc. PbCl2, etc. We have solubility is equal to cube root of Ksp by m raised to n, m raised to 1 raised to 1 into 2 raised to 2, that is equal to 4. Okay, like this. Aluminium chloride, AlCl3 or you know the aluminium hydroxide. What is the situation? Aluminium hydroxide, that is S is equal to, that is 3 plus m plus 1, that is 3 plus 1, 4 raised to Ksp divided by 1 raised to 1 into 3 raised to 3, that is 27. This is equal to 4 root of Ksp by 27. That is the situation. Okay, you have to study this equation. Generally, you are asked to calculate the solubility product of AgCl. Okay, so AgCl solid. Saturated solution. You have say binary electronic AgCl plus aqua plus Cl minus aqua. We have S, yes, what's collected, therefore Ksp is equal to Ag plus into Cl minus. So we have S into S, that is equal to S square, therefore S is square root of Ksp. Square root of Ksp. So this is generally you are asked to calculate. The next is we are to discuss the application of solubility product and common ion effect in analytical chemistry. Okay, short in a brief I will give you the situation, the principle. Okay, immediately. that we can classify various the analysis of cation is convenient for we have two steps for the analysis of the cation from the mixture. One is the separation of the cation from one another in the form of precipitate, and other is the analysis of the cation. Okay. So for the separation and analysis of the cation, we have to make use of common ionic effect and solidity product. When we are usually encountered with more than one cation, a mixture of the cation, we have to separate a particular mixture. Or we have to precipitate a particular cation from the other cation, or we want to precipitate a particular one cation while other cation is to be remain in the solution. That is our aim, or that is our procedure. Suppose we have two cation in the solution, and we want to analyze the two cation. Okay, first you have to separate one cation in the form of the precipitate, and other is to remain in the solution, and then analyze. And then after separating the first cation and its analysis, you go for the analysis of the second cation. That's the situation. Okay. Anyway, in the analytical chemistry, for the convenience of the analysis, we classify the various cation into groups. You know that first group, second group, third group, fourth group, fifth group, etc. like that, and sixth group, etc. All of you familiar with that? The case of second group I wish to explain. The case of second group, analysis second group. We have to analyze various reagents like copper, cadmium, etc. Okay, copper, cadmium, etc. While the third group, we wish to analyze aluminium, chromium, iron, especially ferric. Okay, and the fourth group, we wish to analyze, that is zinc, manganese, zinc, nickel, cobalt, etc. This is the situation. And the fifth, then next group, or you know that fifth group, barium, calcium, strontium, and the sixth group, all familiar, magnesium. This is situation. You consider the case of second group. The second group, we wish to precipitate only copper and cadmium, while all other cations is to be remain the solution. Okay. The group reagent employed are hydrogen sulfide. Mainly, the group reagent employed is an hydrogen sulfide solution, hydrogen sulfide gas, which is the aqueous system furnishes 2H plus and S2 minus, and the metal salt combines with the sulfide ion, and the metal gets precipitated as sulfide, CuS, CDS, etc. So in the second group, we want to precipitate and separate the metal from the solution as their sulfide. Copper has copper sulfate and cadmium has cadmium sulfide. But at the same time, the other metal sulfide, that manganese, for fourth group, the fourth group metal also be using the same reagent H2S. That will give 2H plus S2 minus, and we want precipitate as MNS, ZNS, NIS, and COS. Suppose we have two metal ion salt solution having two metal ion are given like copper and zinc, or copper or cobalt, or copper or nickel, like that. Suppose we have a salt solution containing copper and zinc. First we have to analyze copper, separate copper and analyze it, not separate precipitating this fourth group metal. And after analysis, separation and analysis of the second group only, then you go for the analysis of the fourth group metal. That is it. And for that, we have to make use of. Similarly, on analyzing the second group, we are never allowed to precipitate the third group metal. While analyzing third group metal, we never allow the precipitation of the fourth group metal. So here we are employing the principle of common ionic effect and solidity product. Okay, the main principle is that for the precipitation of the salt from the solution, we have to employ the principle, that is, if the product of the ionic concentration exceed the solubility product of the salt, the solution becomes supersaturated, thereby it gets precipitated. That is the main principle employed. So the minimum condition for a salt to be precipitated is that the ionic concentration should exceed the Ks of the particular salt. You know that? The second group metal, that is sulfur metal, is precipitated as lead sulfide, copper as copper sulfide, cadmium as cadmium sulfide. Similarly, the fourth group metal is also wish to precipitate as a sulfide, as manganese sulfide, zinc as zinc sulfide, cadmium as cadmium sulfide, so cobalt as cobalt sulfide, nickel as nickel sulfide. Generally, what is the situation is that the copper sulfide and cadmium sulfide have low solubility product. They have usually low KSP. While the fourth group metal sulfide have high KSP. That is the thing. But to remember, that is a fact. The second group metal sulfide have low KSP value, while the fourth group metal sulfide has high KSP value. This fact is to be make use of while doing the precipitation by passing hydrogen sulfide. Okay. So the second group metals are precipitated as copper sulfide and cadmium sulfide by passing hydrogen sulfide in the presence of HCl. The presence of HCl. Why? That is the situation. That is, that metal have generally low KSP value. That metal sulfide have generally low KSP value, so that the product of the ionic concentration, should exceed the solubility product of copper sulfide and cadmium sulfide only, and not that of manganese sulfide and zinc sulfide. That is the situation. For that, we have to suppress the dissociation of hydrogen sulfide, so that we are using hydrogen's HCl. When we are passing hydrogen sulfide in the presence of HCl. So in the same group analysis, we are passing hydrogen sulfide in the presence of sulfuric acid, hydrogen chloride. The presence of HCl, because HCl furnishes the common ion H plus ion. Because of the common ion H plus ion, the extent of the precipitation, the ionization of hydrogen sulfide is prevented, suppressed, so that the sulfide ion concentration is considerably less. So that the concentration of sulfide ion become considerably reduced. In that case, the product of the ionic concentration of copper and sulfide now exceed only the copper sulfide and CDS, and will not exceed that with respect to MNS. Okay, that is it. That you have to remember. Suppose we are passing hydrogen sulfide in the presence of HCl, so that the suppression, the hydrogen sulfide dissociation is suppressed to a considerable extent, so that the sulfide ion concentration is considerably less in the solution. In that case, the product of ionic concentration of copper and sulfide will exceed only the solubility product of the copper sulfide, and will not exceed the solubility product of MNS, SL, because they are very high value. Generally, they are a very high value. For that, we have to supply more S2, that is sulfide ion. That is actually doing in basic solution. That is the fourth group metal. We are passing hydrogen sulfide in the presence of ammonium hydroxide. Okay. When ammonium hydroxide is furnished, this ammonium hydroxide furnishes ammonium ion and hydroxyl ion. And the hydrogen sulfide furnishes 2H plus. Okay. H2S ionized gives 2H plus and S2 minus. This OH minus and H plus combines to give H2, 2H2. So that the equilibrium shift to H side, so that more hydrogen sulfide dissociates. Okay. So in the presence of ammonium hydroxide, the hydroxyl ion combines the H plus ion to form unionized water molecules, so that H2S equilibrium is shifted to its right, so that more H2 minus ion is produced. So more H2 minus ion thus produced will help the product of the ionic concentration of Mn and sulfide ion to exceed the solubility product of MNS. Okay, so that they become supersaturated with respect to that's our solution for the case. So that is the situation. I hope that you have followed my explanation. That is, we can adjust the solubility products of the second group metal cation and fourth group metal cation by the common ion effects as required or as we wish. Okay, the second group we wish to precipitate only copper as copper sulfate, cadmium as that cadmium sulfate, and not wish to precipitate manganese as manganese sulfate, zinc as zinc sulfate there. So we have to keep the fourth group metal in the solution itself. For that we have to supply only small amount of sulfate ion, because in that case we have to meet the condition. The product ionic concentration of copper and sulfate become exceed the solubility product of CuS only, because they are generally low value. While the fourth group metal cation we are using ammonium hydroxide, so that we have to furnish more sulfate ion. Okay, we have to increase the dissociation of H2S to get more sulfate ion, so that we have to meet the condition. The product of the ionic concentration of manganese and sulfate ion should exceed their solubility product is usually very high value. So that's it. Similarly, in the case of that the third group metal, we are using ammonium chloride and ammonium hydroxide usually. So to get aluminium as aluminium hydroxide. But in the fourth group metal we are using fifth group we are using ammonium chloride, ammonium hydroxide, ammonium carbonate. All these are, we have to adjust the solubility product as required. We have to precipitate only that metal ion there by adjusting their dissociation as according to your wish, or require to meet the solubility product condition. Okay, thank you very much. So you go through this area, the analytical field, the chemistry, and study well that principle. So time we are finishing my class. So I am winding up the class. So with this class, our Ionic Equilibrium is finished. Thank you very much.